We're going to start our week 2 lectures. So we're going to continue working on examples. So here's a question from summer 2 years ago. So as plotted below, the lines here have unique intersection. So probably just before I drive on, what would be a good thing to do is write these in the form y equal mx plus c. And this one is, you just have to take away the minus 0.001x plus 1.001, and this one is fairly easy to solve because you just 0x is just 0, 1y is just y equal to 1. So remembering that things of the form y equal to mx plus c are lines, we know that these two things are lines, and we know that the slope of the second one, if we actually write it in the form a multiple of x plus a constant, the multiple of x is 0. So that means it has a 0 slope, so it's flat. So that would be the red, in this one, the red line. And then look at the other one, that cuts slightly higher than 1.001, and more importantly has a negative slope, so it's going slightly down. So the blue corresponds to that. And you see they have a unique intersection. If you substitute in x equal to 1 and y equal to 1 into both of these, it'll satisfy both equations. So it's in the intersection. So there's going to be a number of little questions here. So if the 0.001 is rounded to 0 and the 1.001 rounded to 1, then the linear system looks like this. So I'm just saying, okay, round the 0.001 and round the 1.001, correct to actually 3 significant figures, then you get this linear system. So first thing is use Gaussian elimination to find the solution of this and explain it geometrically. So you just have to remember, again, it's probably good if you have the manual in front of you. So I think we ended up with 0x, 1y equal to 1, and 0x, 1y equal to 1. I think, if I'm not mistaken, and that is what we have. Okay. Now we're going to do Gaussian elimination. You cannot get a pivot in the first column, so the first column is actually fine. You have a pivot in the second column already here, and we need to use that to kill what's underneath. So we're going to do row 2 sent to itself minus row 1. So the first row is good, 0, 1, 1. And the second one, so 0 minus 0 is 0, 1 minus 1 is 0, and 1 minus 1 is 0. And this is now in reduced form because you have the staircase. Now the staircase, because there's zeros in the first column, begins a little bit late. But there you go. Okay, so the first question is, does this have solutions? And the answer is yes, it has solutions because there's no row of the form 0, 0, 0, non-zero. So solutions, yes. And next question is parameters. So if there's any column that has no pivot, that corresponds to a parameter. So it's a value, in this case x, that can be anything. So this is x can be anything. And that should make sense soon. So you'll start to understand properly what the parameters actually represent. Now we want to find y in terms of the parameter. So if I look at the first row, it says, actually just says y is equal to 1. Doesn't it? 0x plus 1y equal to 1, so y is equal to 1. So the solution is x, y equal to t1. Now let us explain, so t can be anything. Let us actually explain this in terms of the solution. So we'll just plot the solution. So we have an y-axis, x-axis, and here's y equal to 1, and all for any value of t, so for any point basically on the x, so I mean, okay, let me slow down there. So all of the points have a y coordinate of 1. And then you've got all the possible x coordinates because every single value of t in the real numbers works. So what you end up with is, this is the solution. So for example, you have 0, 1, that's t equals 0. You have 1, 1. You have 1.5, 1. So you have every possible value of in the x coordinate from minus infinity to infinity, that's the real numbers, but all the y coordinates are 1. Okay, now the next question is explain this result geometrically. Now that seems like it is, but remember, if you go back, oh, I forgot a question. We'll have to go back to that one. Sorry, my bad. So these things are lines. So these things down the bottom, these are lines. And the question is, essentially, we've got infinitely many solutions, and why is that? And the answer is that these are actually the same line. So the answer is infinitely many solutions, intersections, because it's the line intersecting itself. So infinite, well, I don't have to kind of explain it all. I'll be looking for you is that they're the same line. So you've just found the intersection of a line with itself, and the changes that you made have made them both the same as the second line, the flat red one, as we see a picture over here in orange. Okay, so that's the first bit done. Happy days. Now the second one is, if you round the 0.001 in the x to 0, then this is the linear system. 0x plus 1y equal to 1, 0x plus 1y equal to 1.001. So let's have a look at this using Gaussian elimination. So we had, was it 0x, 1y equal to 1, and 0x, 1y equal to 1.001. So as before, we can't really do anything with the first column, but we do have a pivot in the second column, and we can kill the thing underneath because we can use that pivot to kill the one underneath. So we're going to do row 2 sent to itself minus row 1. And so we end up with 0, 1, 1. Then we get 0 minus 0 is 0. 1 minus 1 is 0. And 1.001 minus 1 is 0.001. Now you should be getting some alarm bells here because look at the bottom row. Like, we are in the reduced form because we have our pivot, we have our staircase. But look at the bottom row. It says 0x plus 0y is equal to 0.001. That's impossible. So what that implies is that there's no solutions. And the situation was, when you write down the original equations, you assume they have solutions. If you get nonsense, that means that the assumption of solutions was wrong. There are no solutions. So this is a simultaneous equations with no solutions. And how can this happen? Well, again, if we do a little bit of plotting, we might be able to explain this. So again, we'll do a little bit of an x-axis and a bit of a y-axis. And this time, now this picture up in the right hand, that doesn't really explain, like, we haven't drawn the line twice. That's just plotting the solution. Here we have no solution, so there's nothing to plot. So what I'm actually going to do is I'm going to plot the original lines. Well, the lines as they're given. So this one is y equal to 1, and it's 0x, so there's no slope. This is y equal to 1, that's the first one. And then exaggerating, the second one is y equal to 1.001. And I've exaggerated the difference between them. So what you see here is actually there's no intersection between them because they're parallel. And the second part of the question above was explain the result geometrically. Why is there no solutions here? It's because the lines are parallel. Now, what's the lesson here? We've done some rounding of 1.001 to 1 and 0.001 to 0. And what that's doing is it's changing the problem immensely. Now, you could say, oh, you're doing rounding, but actually I haven't done any rounding. I suppose the rounding has happened kind of before I wrote down the problem. And basically the story is, what's the conclusion here? Comment on rounding in the context of linear systems. Rounding can change the answers utterly. Can change solutions, say, dramatically. And this is more than just changing the numbers a little bit, because remember, originally we had a unique solution. The two lines just intersected once. We did a little bit of rounding, and we got the rounding actually made the lines the same. We had infinitely many solutions. And then we did another rounding, and we had no solutions. So not only can rounding really change the answers, so we would have seen that last week, where using 4 significant figure rounding, the answer should have been both around 1, and we got, I think, 0 and 1. So not only can that happen, but the whole nature of the solutions can change as well. You can go from a unique solution to infinitely many solutions to no solutions. So the lesson is you need to be very, very careful in rounding when you're doing linear systems. Okay, now we're going to go back now on the question that we skipped here. Okay, let's have a look at this one. So it's obviously solve. Now I might just note, I'm not sure how this one goes, but I have an idea. So when you write down the equations, you assume that you have a triple of numbers. The fancy way of writing that is in order to the 3. So it's 3 real numbers that satisfy these equations. And if you end up with nonsense, the issue is that you assume there's solutions. So if you get nonsense, there's no solutions. I think that might happen here. Okay. So off we go. So the first equation as a row is 1x, 0y, 10z equal to 5. Then we have 3x plus 1y minus 4z is equal to minus 1. And 4x plus 1y plus 6z equal to 1. So this is where we're at. So what we want to get is pivot, zeros underneath. So the good news for us is that we have a pivot already. And what we're going to use that pivot to attack the things underneath. In particular, we need to turn the 3 into a 0, we need to do 3 minus 3. Now you can't just take away 3, that's not an elementary row operation, but you can use the pivot to do row 2 sent to itself minus 3 times row 1. And similarly, you can do row 3 sent to itself minus 4 times row 1. Now we argued last week that these elementary row operations will not change the solution, but they'll make things easier for us to see. So the first row is still good, 1, 0, 10, 5, and let's do our elementary row operations. Now you'll need practice at these. 3 minus 3 times 1 is equal to 0. 1 minus 3 times 0, so I'm doing 3 minus 3 times 1, 1 minus 3 times 0, minus 4 minus 3 times 10, minus 1 minus 3 times 5, the whole way across. So 1 minus 3 times 0 is 1. Minus 4 minus 3 times 10 is minus 34. And minus 1 minus 3 times 5 is minus 16. And I will do the other one. 4 minus 4 times 1 is 0. 1 minus 4 times 0 is 1. And 6 minus 4 times 10 is 6 minus 40 is minus 34. And 1 minus 4 times 5 is 1 minus 20, which is minus 19. Now you might notice an issue here already. Now what's good is we have a pivot and zeros underneath, and we have a pivot here. We want to turn the thing underneath equal to a 0 as well. So we'll use this pivot here to attack this. So we're going to do row 3 is sent to itself minus row 2. So first row is sound, 1, 0, 10, 5. Second row is sound, 0, 1, minus 34, minus 16. And now we do that elementary row operation. So 0 minus 0 is 0. 1 minus 1 is 0. And minus 34 minus minus 34 is 0. And minus 19 minus minus 16 is minus 19 plus 16, which gives you minus 3. And here you see the issue. if you have a row like this, which says 0x plus 0y plus 0z is minus 3, that's impossible. The left-hand side of 0 can't equal to minus 3. So that's nonsense, which implies the initial assumption of solutions was wrong. There are no solutions here. And that's it. Now, in terms of a picture, it's probably hard to describe what that is. These things are planes. I don't think it's necessarily that the planes are parallel. It can be kind of hard to draw what happens. I think if you imagine kind of a tent, so if you're looking from side on, and one of the planes looks like that, and one of the planes looks like that, and one of the planes looks like that. So there's no point where they all intersect. So I think that's really what's happened here. So like say if this one corresponds to equation 1, this one corresponds to equation 2, and this one, where's the other one? Oh yeah, this one corresponds to equation 3. Now imagine that going into the page, so it looks like a tent, but it goes on forever and ever and ever. So that's like a plan. So the planes are sheets, infinite sheets going on forever. In that picture, you have infinitely many solutions between, so that if you travel along that, it looks like the top of a prism. So you've infinitely many solutions between the first equation and this third equation. It forms a line. You've another infinite number of solutions here between the first equation and the second, and another infinite number of solutions intersection between the second and the third plane. I'll try and draw this another way in a second if you don't understand. But none of them kind of intersect together, so there are actually no solutions. This is probably what happens. So I said I'll try and draw a better picture of this. If you can imagine a prism, now what you have to understand is that these sheets go on forever. So like continue that on forever in that direction and every other direction. So this would be E1, the first equation. Then the floor of the prism goes on forever like that, and then the other face of the prism goes on like that. I don't know if that possibly makes things worse for you, but anyway, there's no solutions there. Okay. So we'll go on to another example. Okay. Now this is nasty enough yoke, and I'll need my calculator here, and I don't know what the space is about. I might start writing up here. I'm not sure about the space. The space is a bit weird. Okay, so solve the following linear system correct to the constraint that all calculations are made correct to 3 significant figures. Now, if you're doing rounding, if you're forced through rounding, you must use partial pivoting because you need some protection against rounding error completely changing the solution, and partial pivoting does that for you. Now what I'll do, I will use the whole page, right? So I'll start up here and I'll write this in augmented form. So now this first frame you wouldn't actually write because we'll explain in a second. So I'll show you the first frame you would write. So if I just write this naively, so I get 0.2x, 0.4y, minus 0.7 equal to 2.66, 1.2x minus 0.1 y, 2.1z, this is going to be painful by the way, minus 5.54, and then 1x, 1y, 1z equal to minus 2.05. Now if you are not doing, of course the other thing is like the figures that go into the equation could be rounded as well, so that's another source of error. So what we want to do with this is we want to turn whatever is up here into a 1. If you're doing exact arithmetic, you can just divide by 0.2, but what we showed last week is that when you're rounding, you want to avoid dividing by a small number. So what we're going to do instead is we're going to change things around so that we're dividing by the biggest possible number, which should be 1.2. So you're going to do row 1 swapped with row 2. Now what you don't have to do, and I actually don't recommend it, is kind of put them in order 1.2, 1 and 0.2, because there's only one of them you're dividing by. And as you'll see, sometimes if you do that, you'll have to do an additional pivot later on, which we'll talk about. So I don't actually recommend that you write this frame. You look at this and you just identify just find the biggest possible number and put that one first. So before writing it in, you do the partial pivoting, you swap row 1 and row 2, rather than wasting your time writing that. Okay. So we get, in that case, 1.2x minus 0.1y, 2.1z equal to minus 5.54. Now, if I make any mistake in this, I'll tell you now. I'm not doing it on purpose. It's just a little itty bitty arithmetic. No, I'm just okay. So I want to turn the 1.2 into a 1, and I do it by dividing by 1.2, and now I'm not dividing by a relatively small number, so I'm in good nick. So I'm going to do row 1, excuse me, sent to itself divided by 1.2. And now remember that the problem is set up in such a way that you have to round to 3 significant figures, and this is actually just kind of simulating, like if you're using a computer. Now a computer can probably do 16 significant figures, but hopefully you get my drift. Okay, so I just have 3 significant figures in this bit. So 1.2 divided by 1.2 is 1. I could put 1.00 if I wanted. There's no real need. Minus 0.1 divided by 1.2, the 3 significant figures, is minus 0. I possibly need more space here. We'll drive on. 80833. 2.1 divided by 1.2 gives me 1.75. Yeah, it's not ideal, my apologies. And then the last number there, minus 5.54 divided by, you can see why this is nasty, divided by 1.2, the 3 significant figures, minus 4.62. Okay, now what I want to do is I want to turn the 0.2 and the 1 into zeros. So I'll turn that into a 0 and that into a 0, and I'll use this new pivot here to do that. So I'm going to do, and hopefully you're kind of starting to see the pattern, row 2 sent to itself minus 0.2 times the new row 1, and I'm going to do row 3 is sent to itself minus row 1. And hopefully I have space over here. Not a great job by me. So yeah, we'll do the row 2 first. So 0.2 minus 0.2 times 1 gives me 0. That's good. 0.4 minus 0.2 by minus 0.0833. 3 significant figures, 0.417. And then minus 0.7 minus 0.2 times 1.75, 3 significant figures, I get minus 1.05. And then 2.66 minus 0.2 times minus 4. I hate numbers like this. 3.58. And then the last one is a bit easier. So row 3 minus row 1. The new row 1. 1 minus 1 is 0. 1 minus that number there would be 1 plus 0.0833, which the 3 significant figures would be 1.08. And 1 minus 1.75 is minus 0.75. And then the last one, minus 2.05 minus that number, minus a negative is plus 4.62. I get 2.57. How bad? Right. Now, let's see. I'm just going to pause and check my work. Okay, I hope everything's going well here. Yeah. So now what I want to do is I want to make another pivot here. But to make that pivot, I'd have to divide by 4.17, but I should be dividing by the bigger of the numbers, which is 1.08. I'll just explain why I'm a bit worried, because when I look down here, it says It wasn't necessary here, but it might have been necessary to pivot the second row as well. Now I'm not sure what actually happened here that caused this to happen. I wonder, did I put them in order last time? Maybe I just put them in for the crack, put them in order, but there's no real need. I mean, you could have put them in order. In other words, put it 1.2, 1 and 0.2, and then if you did that, it worked out, but also it might not have worked out. So my advice is not to bother putting them in order. It just turns out you have to swap them here. Okay, so the issue here is you want to turn that 0.417 into a 1, but you don't want to divide by a small number, a relatively small number. You want to divide by a relatively big number. So we're going to swap row 2 and row 3. So if I do that, first row is sound. This used to be a wicked question to put on an exam. Imagine the exam and you're dealing with these decimals. I actually, what year is this? Yeah, I think this was the last time I put such a question. Now, you have it in your assignment, but that's different. You don't have the same pressures. If you were kind of smart here, you could actually turn the 1.08 into a 1 as you go. But we won't, we'll take our time. Okay, so now what we're going to do, now we seem to have plenty of time, so our space, I'll use it. So now what we're going to do is we're going to do row 2 sent to itself divided by 1.08, and we've avoided dividing by the small number. So first row is fine. 1 minus 0.0833, 1.75 minus 4.62, and then divide row 2 by 1.08. I get 0, I get 1. Now I go to the calculator. Minus 0.75 divided by 1.08, which is minus 0.694. And I get 2.57 divided by 1.08. I get 2.38. Happy days. And now I want to kill the 0.417. So I'm going to do row 3 minus 0.417 times the new row 2. So I got this pivot and used it to kill the things underneath. And now I have this pivot, I'm going to use it to kill the things underneath using this row operation. So I have 0 minus 0.417 times 0 is 0. 0.417 minus 0.417, the dash here means I'm doing, so this row here, sorry, I don't know how to get a cursor, but this row here minus 0.417 times this row here. So I get 0.417 minus 0.417 times 1 gives me 0. Into the calculator now, and I'm being very careful. Now I'm not great at the calculator, but we'll see. Minus 0.694. To 3 significant figures I get minus 0.761. And the last one is 3.58 minus 0.417 by 2.38, which is 2.59. Actually optimistic. Now when I paused the video, I threw the equation into some software, the simple linear system, so I know what the answers are supposed to be. And now all I have to do is turn the minus 0.761 into a 1. So I'm going to divide row 3 by that. Now you could, you might notice there's kind of shortcuts where you don't have to write the first 2 rows again at this point, but I will just to for completeness. It's tough on the space. Now is significant figure rounding, not decimal places, and that's what we'll nearly always use. 694, 2.38. 0 divided by anything is 0, 0 divided by anything on 0 is 0, minus 0.761 divided by itself is 1, and then 2.59 divided by minus 0.761 gives me minus 3.40. So now I'm in a good position. I have solutions. Now, if there's rounding, it's going to be set up in such a way that there's unique solutions, because it's so precise to have no solutions or infinitely many solutions. It's such a delicate state of affairs. Like if you imagine the prism where all the three planes kind of have to be kind of orientated in such a way, if you adjust one of them even a little bit, you're going to have a unique solution. So there's nearly always going to be a unique solution. There's definitely solutions here. Look, we'll just say there are. I'm just saying that whenever I give you one of these, there's going to be solutions. When I say one of these, I mean one with rounding. So now we need to find the solutions. So the first, or rather the last, we work from the bottom. It says 1z is equal to minus 3.40. Done. The second one then says y minus 0.694z is equal to 2.38. Now I'm going to go a little bit fast here. So what I'm going to do is I'm going to say y is equal to 2.38, and I'm going to add the 0.694z to both sides. So I get on my calculator plus 0.694 times z, which I know is minus 3.40, and I get out y is equal to 0.0204. Now you might be wondering why am I doing the approximations? Well, obviously in a context where you're rounding, all these things are obviously only approximately equal, and it's all implied equal to 0.0204 to three significant figures. And then the first row reads x minus 0.0833 times y plus 1.75 times z is equal to minus 4.62. And again, I'm going to kind of use the calculator here. And I get x is equal to, so I'm doing the minus 4.62. I'm going to add 0.0833y to both sides, and using the fact that y is 0.0204. And then take away 1.75 times z, and z is minus 3.4. And I get an answer here of 1.33. Okay, so I have an answer here that, and I'm going to actually give you the exact answer using exact arithmetic, because it can be done, because the decimals could be converted into fractions. So using computer software, I know the exact answer. Well, I have the exact solution. It's written there, and I can convert that. They're in fractions, but I can round them. So the exact solution is x, y, z to three significant figures is 1.35. That's actually exact. Then y is actually a fraction, but it's coming out as 0.00909. And the z is coming out as minus 3.41. Now what you're seeing is that you do have differences between them. Like there's a fair bit of difference between the two y's. That's probably got the largest percentage error, but overall it's kind of capturing the solutions quite well. But if you didn't do partial pivoting, the odds are you'd have big differences. And y here and the approximation with the rounding the whole way through, and the one where you get the exact answer and round, like they're both pretty much close to zero. I mean, 0.02 and 0.01, there's not much between them really. So it's quite accurate. Okay, so here it says, oh, it was necessary to pivot.